All right, let's dive right in. We're going to tackle a mystery that's not just fundamental to chemistry, but it's beautiful. We're talking about the secret behind color itself. Have you ever really stopped to think about why some things are so incredibly colorful? Like, why is copper sulfate solution that brilliant blue? Or how do rubies get that stunning deep red glow? It all points back to one group of elements, the transition metals. But what's their secret? What is it about them that literally paints our world? Well, the answer, believe it or not, is hidden in the invisible electric fields that surround these metals. And we have a key to unlock this secret. It's a surprisingly powerful model called crystal field theory. Okay, so what I love about this theory, let's call it CFT for short, is just how elegant, how simple it is. It kind of sidesteps all the messy, complicated details of chemical bonding. Instead, it makes this really bold, simplifying assumption. It looks at all the molecules hanging around the central metal ion, we call those ligands, and it says, you know what? Let's just pretend they're tiny little points of negative charge. That's it. And from that one simple idea, the whole theory just unfolds. The entire magic trick is about how this electric field from the ligands interacts with the places where the metal's outermost electrons hang out, the orbitals. And we're going to be focusing on a very special set of 5 of them, known as the d orbitals.
So here's where things get really interesting. This interaction causes something totally unexpected to happen. Those d orbitals, which are normally all at the same energy level, they get split apart. They're forced into different energy levels. Let's dig into how that actually works.
First, picture a metal ion just floating out there in space, all by itself. In this state, its 5 d orbitals are all perfectly equal. They have the exact same energy. The fancy word for this is degenerate. Think of it like 5 identical apartments on the same floor of a building, all the same, all at the same level. But then the ligands arrive. Let's say 6 of them approach in a nice, symmetrical octahedral shape. Suddenly, things are not so equal anymore. 2 of those d orbitals, we call them the EG set, find themselves pointing directly at these incoming negative charges. Let's go back to our apartment analogy. These are the 2 apartments whose windows are now facing a super loud construction site. There's a ton of repulsion. The other 3 orbitals, the T2G set, they get lucky. Their windows point between the construction sites, so they avoid most of that direct negative repulsion.
And this is the result. It's perfect. Those 2 unlucky EG orbitals, the ones with all the repulsion, they get pushed way up to a higher energy level. They're destabilized. Meanwhile, the 3 lucky T2G orbitals actually drop down to a lower, more stable energy level. And just like that, the 5 identical apartments are gone, the degeneracy is broken, and that energy gap between the high and low levels, that is the absolute heart of this theory. We call it the crystal field splitting energy, or just delta O for short. Okay, so we've split the orbitals. We've created these new energy levels. The next logical question is, where do the electrons go? How do they decide where to live? And this leads to another really fascinating choice they have to make. Let's say we're dealing with a metal that has 4 d electrons we need to place. Now, electrons are kind of lazy. They always want the lowest energy spot they can find. So the first one goes into one of the low-energy T2G orbitals. The second one goes into another one, and the third fills up the last one. Notice they each tick their own orbital. They prefer to have their own space before they're forced to pair up. That's a fundamental idea called Hund's rule. Okay, so far, so good. Simple enough, right?
But now we hit a dilemma. What about that 4th electron? It's standing at a crossroads and has a huge decision to make. Does it pay an energy penalty to squeeze into one of those already occupied low-energy T2G orbitals? Or does it pay a different energy penalty to make the big jump up to one of those empty but much higher energy EG orbitals?
And really, it all boils down to simple economics for that electron. It's a cost-benefit analysis. If that energy gap, that delta O, is pretty small, which happens with what we call a weak field ligand, then it's actually cheaper for the electron to just make the jump. It takes less energy to move up than to pair up. This feeds us what we call a high-spin complex with lots of unpaired electrons. On the other hand, if that gap is huge from a strong field ligand, then the jump is just too expensive. It's cheaper to pay the smaller pairing energy and double up in the lower level, and that gives us a low-spin complex.
So you're probably asking, how do we know if the field is weak or strong? Well, it all depends on the ligand. Chemists have actually tested this out and ranked ligands based on how big of a split they cause. It's called the spectrochemical series. It's like a cheat sheet. On one end, you have weak field ligands like iodide,
which cause a tiny split and lead to high-spin complexes. On the other extreme, you have super strong field ligands like cyanide, which cause a massive split and always favor low spin.
Okay, we have all the pieces now. The splitting, the electrons' choices, everything. With this toolbox, we can finally get back to our original question. We're ready to explain the magic of color, and as a bonus, we can even understand invisible forces like magnetism.
Let's look at a perfect real-world example. Two complexes of iron. First, you have iron surrounded by water molecules. Water is a pretty weak field ligand, so the energy gap is small. The electrons say, it's easier to jump, so they spread out into a high-spin state, leaving us with 4 unpaired electrons. Now, swap the water for cyanide. Cyanide is a super strong field ligand, so the gap is enormous. The electrons say, no way I'm making that jump, and they all pile into the lower level, pairing up. This gives us a low-spin state with 0 unpaired electrons. Think about that. Same metal, just different neighbors, and you get a completely different electronic reality. And here's the best part. This isn't just some abstract theory. You can actually measure this stuff in the lab. Each of those 4 unpaired electrons in the water complex acts like a tiny little magnet. So the whole complex is strongly attracted to a magnetic field. We call that paramagnetic. But the cyanide complex, with 0 unpaired electrons, it has no tiny magnets. In fact, it's slightly repelled by a magnetic field. That's called diamagnetic. Crystal field theory predicts this behavior perfectly. It's amazing.
And now, finally, the big reveal, the color. It all comes back to that energy gap, delta O. When white light, which contains all the colors, shines on one of these complexes, something cool happens. An electron in the lower T2G level can absorb a photon of light, but only if that photon has the exact amount of energy needed to make the jump up to the EG level. So the complex essentially eats that one specific color of light. What do our eyes see? We see all the colors that weren't eaten, the leftover light, which appears as the complementary color. So a tiny gap absorbs low-energy red light and looks green. A bigger gap absorbs yellow light and looks violet. The size of the gap literally dictates the color of the compound. That's the secret.
And you know what? This powerful idea goes way beyond the simple octahedral shape we've been focused on.
You can apply the very same principles to figure out what's happening in other shapes, like tetrahedral or square planar complexes. They each have their own unique way of splitting the d orbitals. The theory is even powerful enough to explain some really weird phenomena, like why some perfectly symmetrical molecules will suddenly twist or distort themselves just to become a little more stable.
Now, of course, no scientific model is ever perfect, right? The biggest strength of CFT is its beautiful simplicity, but that's also its biggest weakness. By pretending ligands are just little negative dots, it completely ignores that the bonds between the metal and the ligands are more complicated, that there's some sharing of electrons going on. For that deeper, more accurate picture, you have to move on to more advanced ideas like ligand field theory. But still, you just can't deny the power of crystal field theory. It's such a perfect example of how a simple, elegant idea can give us incredible insight into how the world works. And it really makes you wonder, doesn't it? If a straightforward model based on electric fields can explain something as beautiful as color and as invisible as magnetism, what other elegant, simple rules are out there just waiting for us to discover them, hiding right beneath the surface?